So, also let's talk about potassium 40. You have potassium 40 in your body. It basically gives off radiation, beta particles and some gamma rays. This stuff, if you sleep with someone for a whole year next to them every night, not for a whole year, but every night, then they get exposed to radiation from you and you get exposed to radiation from them, from the potassium 40 component, which adds up over the year to about 0.02 millisieverts a year, or 20 microsieverts of radiation by sleeping with someone, which is equivalent to a hand x-ray. So you don't, and these are delivered at 2 different dose rates, right? This is over a year and this is all at once, but still the total dose to the organism is the same, whether you sleep with someone or get a hand x-ray. All right, so let's talk about some other occupational exposures. I put this in here because I'm standing here holding a fuel bundle that's about to go into a CANDU reactor. Okay, so that's a fully loaded uranium fuel bundle. These are fuel handling units. These are guys, this is the face of the reactor. That's going in the reactor. Holding that fuel bundle like up against my chest is going to give me about 40 microsieverts per hour. But if I hold it in front of me at 1 meter, it's shielded, the atmosphere is shielding me from the radioactivity that's coming off the uranium. And I get about 4 microsieverts per hour holding that thing at a meter. Like I can't hold it there for an hour because it's about 70 pounds or 65 pounds. So, but anyways, it's there and these things are doing the same thing.
But these are micro, not milli.
These are microsieverts, that's right. So what does that mean in terms of what you guys get, pilots and aircrew? Well, that was in that brochure. Here's what you get at the high end in the 777 series. Highest dose rates, microsieverts per hour, 7, 6, 7. That's actually more than holding the fuel bundle, right, per hour. But on the low end, it's there. So again, you have these calculations based on modeling that can give you different sort of calculations on dose, but somewhere between, high of 7.5 down to a low of about 2.8 in this series of planes that however you guys operate these things. That dose rate per hour is the same as me holding a fuel bundle at 1 meter. Right there. So if you ask someone what's more dangerous in terms of radiation, they're going to say the fuel bundle, presumably, right? I would say. But in fact, that's what it's ironic that the dose rates are almost exactly per hour at 30,000 feet with a fuel bundle at 1 meter or sitting on the airplane. Just to put that in perspective for you. It doesn't mean that that's bad. It just means it's really low, both situations. Now this will give me a chance to segue into the medical exposures, which is 50% of our average exposure over our lifetimes as humans. The reason I say it that way is because if you have to go and get a couple of CT scans, all bets are off because you're not even on this chart anymore, right? You've given yourself radiation doses that are 10 times higher than what you get over your entire lifetime if you didn't have to get a medical procedure done. So, but we still say on average, we take the whole population, all the people, and say, you're getting exposed to natural stuff, and some people are getting exposed to medical stuff, but on average, this is the dose for the population size. This is what the dose rates are going to be. About 50%, you could say, comes from this source. So here it is again in a graphic form. I showed you this before. What makes up the big chunk of the half of the man-made stuff? There it is there. Nuclear medicine and x-rays. They make up a big chunk of it. The other man-made stuff, nuclear fuel cycle, fallout, occupational exposures like you would get flying an aircraft, are very small compared to when you put in the mixture of medical. This is just medical exposures. This is not therapy. This is not therapeutic doses. This is sort of diagnostic doses. X-rays, nuclear medicine, things like that.
Therapeutic doses are a lot higher.
Oh yeah, thousands of times higher. But we're trying to kill things there, tumors and stuff. So I'll start with my first little slide of my kids, and I'll talk about medical exposure. I'll start at the low end of medical exposures. This is what's called dual X-ray absorptometry. This is over here in the hospital at McMaster. This thing scans us, looks at our bones, and tells us how dense our bones are. It's bone mineral, bone density studies, and tells us how our bones are sort of mineralizing and demineralizing. And they don't have a lot of young children that are so-called normal, healthy. So whenever we get a chance to bring in normal, healthy kids, we do. These are my kids. Happened to be a snow day on February 6th, so they get to go to the hospital and volunteer to get irradiated, and they did. They were happy about that. You can tell they're smiling. Well, there's the dose from a banana. So that's 1 microsievert, right, roughly, from potassium 40 at these decays if you ate a banana. What did they get from the DEXA scan is, there's the DEXA scan, that's Roberta. And yeah, well, I'll do the math for you. So don't want to overtax you today, in this seminar. But that's roughly equivalent doses of radiation for the bone scan versus the eating the food that's radioactive. So I guess the point I'm trying to make is that people would actually, some of them were very mortified by the fact that I took my kids to McMaster and irradiated them on their school day, but in effect we were getting some good information, and it worked out fine. X-rays. We go and get a chest X-ray. We get a whole body X-ray to our chest. We get about 1 millisievert, or 1 milligray. Because it's X-rays, I can call it a gray, because remember, sieverts and grays are the same when we're talking about X-rays or photons. This is a mammogram, so women go get annual mammograms. They will get about 1 millisievert or 1 milligray worth of dose. And this is, I have to put this up because when I say you get a chest X-ray, it's about 1. That ranges from about 0.01, depending upon the instrument you're using, up to 100, depending upon the procedure. Studies have been put out that show, depending upon the procedure you're getting, the instrument that they're using, the image they want to create, you can get a large, many orders of magnitude difference in dose from the same thing. So just by saying an X-ray gives you about 1 milligram, I put that up there as a baseline, but it can go either side of that 10 times or 100 times. All right? It's hard to keep track of these doses, but I'm just putting it this way just to give you relative proportions that X-rays in general are relatively low, mammograms relatively low. A CT scan, CAT scan, which is a series of X-rays, multiple series of X-rays, will add up in dose because you're doing many slices through a person's body. This is a slice through the person's body, through the chest cavity here. You get the heart in the middle, the spinal column, the vertebrae, and then the lungs. We've got some issues here with the lung with no tissue there, emphysema. There's a tumor in this person's lung, and it's my favorite slide because it has the cause of the tumor probably in his pocket of his shirt, and it's a full pack too. So, anyways, it's regrettable, but that's what causes smoking causes lung cancer in general in some people. Anyways, the dose from that adds up. So you get 10 to 40 millisieverts or milligray dose from that particular procedure. So if you go get one CAT scan is about 10 years of flying worth of radiation. If you get one. Most people don't get one. You get 3 on average because you go find something, you treat something, you have a look and see if it's there, and you go do some follow-up. So it then puts all this idea of what is risk, kind of blows it out of proportion a little bit. I don't know if you have to get regular X-rays as a pilot. I know when when we were uranium mining in Elliott Lake, you had to get regular chest X-rays every year, which I'm sure added up to the dose way more than the mining was. And of course, we have other procedures that are getting more complicated where we combine a CAT scan with a PET scan. Remember the first slide I showed you of the lung tumor was a PET scan. This is a PET scan here in color. It can add up to into even higher doses from these diagnostic imaging procedures. I can put this up. I found this picture a while back. It was published in a book in 1989. I can't find out when it was actually taken. It's hard to see, but it's airport security at French Customs. There's an open X-ray tube right here. This guy's holding a fluoroscopy screen looking through it. And there's a suitcase between the source and the screen. And they got a whole bunch of other stuff they're going to look at over here on its way to the States. I don't know what kind of dose they were getting there, but I can assure you it probably was a high dose if you're doing that every day.
It looks like the 1800s just from the...
It does. Yeah. But it can't be too 1800 because we didn't actually invent X-rays until 1895. So probably early 1900s. But these guys, this is the time when we didn't really understand how these things worked, and lots of people had lots of tissue damaged and things happened in those days. But I thought I'd bring up body scanners because that's a big thing, right? We have to worry about, when you go through the scanners, there's the 2 types of scanners. You've probably heard about them. One uses microwaves, which can look through your clothes, do a surface analysis, or low energy X-rays. The low energy X-rays can penetrate the stuff and you get your image produced, so we can see things hidden under clothes like that, which would be very bad for her to be carrying that gun like that and things. But if you want to talk about doses, if you're going flying and you're going through this thing, or you're air crew and you're going to go through one of these scanners, I don't know if you have to or not, but I do usually. I usually pick it. If I have a choice, I'll say I'll take the scanner, just go in there and get some X-rays. How much dose do you actually get? People are worried about it. Delivers about that a single scan, which is tiny, and it's about 2 minutes of flying at 30,000 feet, or less, maybe a minute, depending on where you're flying.
There's been a question about whether or not, because that amount of in that case, microsieverts is over such a small dermal depth, that in fact it is considered a more of a problem? Is that accurate or not?
That would be a good hypothesis, but there's no data to support that at all.
Like none.
Especially at those doses, because you have to understand that that's like saying, I can't even do the math, but it's about 1 cell in every 10,000 are actually going to get a photon hitting it.
Right, yeah. It's
At 1 millisievert, so 1 millisievert, this is microsieverts, every cell on your surface of your body might get 1 photon.
right.
So it's not even, like, it's such a tiny amount. Some people are arguing that maybe because the lens of your eye is particularly sensitive, that you might want to close your eyes. But you're going to close your eyes for the whole freaking flight across? So you got a problem there. All right, so let's look at some, okay, we'll look at some epidemiology, just sort of a high-level look at what we kind of know as of today. And we'll just start off with this first one. So I'm going to go back. This guy, John Boyce, is a well-known, very reputable epidemiologist, and he put this out in 2000 in a journal called Health Physics, and they looked at epidemiological studies in pilots and aircrew. And I put this on there so you'll have a reference to it and you can read it. But the bottom line is this: back in 2000, epidemiological studies conducted over the last 20 years provide little consistent evidence linking cancer with radiation exposure from air travel. So basically what he's saying there is we don't have any evidence epidemiologically 10 years ago that the past 20 years have caused any increase. We have sort of no evidence to suggest that there's some negative effects from radiation. He points out specifically from radiation exposure. Another one more recently, 2008, put out in London, Cosmic Radiation in Commercial Aviation. Epidemiological studies of flight crew have not shown conclusive evidence for any increase in cancer mortality or cancer incidence directly attributable to ionizing radiation exposure. Again, no increased cancer risk from ionizing radiation. Another study put out more recently, 2009, ionizing radiation is considered to contribute little, if at all, to elevated risk for cancer among aircrew, whereas excess ultraviolet radiation is a probable cause for increased melanoma. So there is increased risk, but the last sort of the sort of major epidemiological reviews looking at cancer risk associated with radiation exposure have not shown anything. But the question is there increased risk for others? Is there an increased cancer risk or other type of risk in pilots and in aircrew? And this is the first sort of mention of increased melanoma risk. Well, it's been established that there is increased melanoma risk in aircrew and in pilots, probably because of ultraviolet radiation, because there is known to be an increased melanoma risk for aircrew and pilots.
Does the aircraft structure not shield you from ultraviolet?
It has to do with what you do in your leisure time.
Okay.
That's what they claim.
All right.
I'll go back to the study back in 2000. So I'll go up one sentence. For example, there is an increased risks of certain types of cancer in aircrew and in pilots. And so, for example, increased rates of breast cancer among flight attendants has been attributed to reproductive factors such as nulliparty, which means they don't have as many children on average as other women do. So having babies is well known to actually reduce your risk of getting breast cancer. But if you don't have babies, your risk goes up. So there is an increased risk associated with breast cancer, and they're attributing it to the fact of the lifestyle of the aircrew and the attendants increases their risk. It's not much. It's a tiny, tiny increase in risk. But if you can show an increase in risk due to an occupational sort of, I wouldn't even say it's occupational, it's probably more behavior associated with the occupation you have, you're going to increase your risk one way or the other. So you can actually go on and figure out that these things actually increase your risk. And then the other thing is, increased rates of melanoma among pilots have been attributed to excessive sun exposure during leisure time activities. So you have increased cancer risk. And so the first thing we do is cause and effect, right? We have a cause, we have an effect, which is cancer, increased breast cancer in attendants and increased melanoma in pilots. Well, what's the effect? Well, there's radiation from flying, so it must be radiation. But in fact, you can do some nice epidemiological studies that shows it's not the radiation, it's something else that's causing the increased risk. Just a couple of papers just came out, ultraviolet light and blue light. This is for civilian pilots. There is an increased risk of cataracts and stuff caused by not wearing sunglasses. And then this one here is talking about one of the biggest risks we have in terms of cancer. We know that perturbations to your circadian rhythms or your diurnal cycles, in other words, sleeping when you're supposed to sleep and being awake when you're supposed to be awake, is a good thing. If you screw that up a lot, if you actually do a lot of night shifts, if you work shift work, if you do long sort of periods where you don't sleep and then long periods where you do sleep, that changes your circadian rhythm. That definitely has effect on risk associated with certain diseases. So they're talking about that now as being one of the risk factors. I'm not saying this is a negotiating thing you can deal with when it comes to negotiating, but it is a lifestyle. And I just pulled up one sort of slide where this was a thesis someone did, and they just, you didn't really need to look at this, but it was just challenges facing airline pilots. And I just went through the whole things that you guys have to go through as pilots, and it causes physiological and psychological stress, a lot of these things. So these things will also play a role in terms of your risk of getting diseases, in terms of occupational, your occupation, but it's not related to the one component we all think about, the radiation in flying. All right, I'm going to just talk to you about how do we actually try and calculate your risk. This should take a few minutes. Is that clock still working?
Yeah, I can hear it ticking.
Is that the right time?
It is.
All right. I had to wind that up at the start, so it's it's not. I got that off. I'll talk about that in a minute. All right. So the way that we have to talk about risk and the way that risk is calculated is based on a hypothesis that's been used for many, many years, and is still being used today in many situations, although it's being challenged from many different directions. And that's called the L&T hypothesis, which means linear no threshold hypothesis. And this hypothesis is a very simplistic way of looking at how radiation works with us. It's a model, it's a hypothesis that says that dose is additive. Well, okay, so we can add up dose. We can add 10 plus 10 is 20, and 20 plus 20 is 40, and we can add up the dose, and the dose is additive. It also says that the risk associated with the dose is additive. So if a small dose of 10 has this risk, if we double that dose, we can add that up. We can also double the risk associated with it. So dose is additive, risk is additive. There is no threshold for risk. That is, no matter what dose of radiation you get exposed to, it carries with it some level of risk. There is no threshold. The threshold means below a certain point, there is no effect. I'm just telling you what the model is suggesting. And it says we're all the same with respect to risk. So biological factors, environmental and biological and genetic factors do not play a role in the risk. It's just the dose of radiation that matters in this model for predicting your risk.